Welcome to our presentation on understanding dynamic and static processes in building automation system. In the realm of BAS, processes can be broadly categorized into the dynamic and static. Dynamic processes involve systems that evolve over time, relying on past or future inputs, while static processes remain stable and do not require continuous adjustment. However, the distinction between the two isn't always clear-cut, with processes often exhibiting both behaviors based on the context. Today we will delve into modeling techniques for both types of processes, including regression analysis for static processes and methods like time series analysis, mathematical modeling, and machine learning for dynamic ones. We will also explore important parameters like prediction horizon, sampling frequency, and lagged variables, crucial for accurate forecasting. Join us as we unravel the complexities of dynamic and static processes in BAS, offering insights into predictive modeling using artificial intelligence and machine learning techniques. Let's dive into the world of dynamic and static processes, exploring how they shape our understanding in complex systems. Dynamic processes are like ebb and flow of tides. They evolve over time, influenced by past and future inputs. Think of energy consumption fluctuations or weather patterns. These dynamic systems require continuous monitoring and adjustment. On the other hand, static processes remain stable or change very slowly over time. Regression analysis is a power tool for modeling static processes, helping us understand relationships between variables. It's like fitting a puzzle together, revealing hidden patterns and dependencies. Dynamic modeling involves time series analysis, mathematical equations, and machine learning. Time series data unveils trends while mathematical models simulate behavior. Machine learning algorithms learn from historical data, predicting future outcomes. To predict dynamic behavior, we define parameters, prediction horizon, sampling frequency, and lagged variables. Then we choose models, recurrent neural networks or deep learning. Seasonality matters too. Understanding cycling patterns ensures accurate forecast. In summary, mastering both dynamic and static modeling empowers us to bridge business needs with technical solutions. Let's dive deeper. Process dynamics, integral to building automation system, encompasses the study of system behavior over time. Dynamic systems, reliant on past and future inputs, play a crucial role in BAS, influencing control strategies for optimal performance. Conversely, static processes maintain stability without temporal dependencies, ensuring consistent conditions. The static system is also called memoryless system. However, distinctions between static and dynamic processes aren't always clear-cut, with some parameters exhibiting both behaviors based on context and time scale. When modeling static processes, we create mathematical or statistical models that describe relationships between variables assumed to be fixed over time or changing very slowly. One common approach in a regression analysis where we identify influential variables and estimate their impact using techniques like linear or logistic regression. The resulting model helps predict outcomes and understand contributing factors. Other methods include structural equation modeling, decision trees, cluster analysis, and factor analysis, each tailored to specific research questions and data characteristics. Choose wisely to unlock insights. When modeling dynamic processes, we create mathematical or statistical models that describe how variables change over time and interact with each other. Time series analysis helps identify patterns and trends, while system dynamics modeling explores complex interactions. Other methods include differential equations, Markov models, agent-based modeling, and machine learning algorithms. Choose the right tool for your research question. Dynamic process modeling serves as a crucial purpose in understanding, predicting, optimizing, and making informed decisions. By creating mathematical or statistical models that capture how variables change over time, we gain insights into complex systems. Wherever it's forecasting energy consumption in smart buildings, unraveling intricate interactions, or choosing the best strategies, dynamic modeling empowers us to navigate the ever-evolving landscape of data and make impactful choices. When modeling dynamic processes, keeping in mind forecasting, key parameters like prediction horizon, sampling frequency, lagged variable seasonality, and trend significantly impact accuracy and reliability. Choosing an appropriate prediction horizon and sampling frequency is crucial, while incorporating lagged variables captures past influences. Accounting for seasonality and trends improves prediction quality, especially in processes with recurring patterns and overall changes over time. Balancing these parameters ensures robust prediction tailored to the dynamics of the system at hand. To predict dynamic processes using AI or machine learning, the process begins with defining the problem and identifying input-output variables. Next, data collection and pre-processing ensure quality inputs for training. Selection of the suitable model follows with training of pre-processed data and evaluation of its performance. Metrics like accuracy guide model refinement. Finally, the trained model can be deployed for real-time predictions with ongoing monitoring for accuracy and adjustments as needed. At the end of each unit, you will find several questions to test your knowledge. Here's one of the questions. What is the relationship between data and information? The answer lies within the materials covered in this unit.